The Art of Messing Around, Episode 5. In my YouTube channel, there's a playlist called Different Kind of Arts in Mathematics. So there are already 4 videos which I really like, and I definitely recommend you guys to check those out as well after this video. And in this one, we are gonna, I'm gonna give you a kind of a reason why this series needs to be true. I think most of you guys have heard about this other one, right? If you just multiply both sides from -1, so you get this series, which is half. In this video, I'm gonna show you why the other one, the counterpart, is -half, which is the same thing. And then, yeah, so in this video, what we're actually gonna do is, I'm just gonna play with Fourier series of some polynomials, like let's say x and x square, right? And like while I'm playing with them, I will discover something new. Like all the other videos in my channel, like the other videos in the playlist Arts Messing Around, but they're also like I'm just playing around with different maths ideas, and then like accidentally I find something interesting and something new, right? So the similar is the case here. So today I'm gonna play around with the Fourier series of f of x equals to x, right? On 0 to 2 pi, and after that it's like 2 pi periodic. Okay, fx equals to x for, so if x belongs to 0 to 2 pi, then it's defined as fx equals to x, and outside this domain it's just the copy of the same function, right? So it's just 2 pi periodic, so we just copy the same function outside this domain. So we want to find its Fourier series, right? So I guess you guys know how to find the Fourier series. Now we know that every function f of x, which if let's say it's a 2 pi periodic, can be written as some constant plus sum from n equals to 1 to infinity an with cos of nx. This is only for 2 pi periodic function because this cosine is 2 pi periodic, right? So then f of x will also be 2 pi periodic, okay? And then plus n equals to 1 to infinity bn sine of nx, okay? And now over here, if we want to find the coefficient, like for a naught, a sub n, b sub n, for any function, we know how to find that. A naught is just 1 over 2 pi integral from 0 to 2 pi of f of x dx, and the an is 1 over pi, right? This is half the interval, yeah, 0 to 2 pi, and then f of x with cosine of nx dx, right? And then for b of n, this is 1 over pi, 0 to 2 pi, f of x with sine of nx dx. So first of all, what I'm gonna do is I'll find the Fourier, the series for this function, fx equals to x, and then I will also find for x square, which I will not show you because I've already done that in the text time. And then I'm gonna be like why do we really need to find out the series for x square separately? Can we not find from the series of fx equals to x? I'm gonna try that, and there is a way. So I will try. So I will use a way to go from the series of x to x square, and also come back from x square to x, and then on the way we will find something. So that's the entire journey for this video. So let's begin. So let's find for fx equals to x. Okay, so we will do this one, Fourier series for fx equals to x, for x belongs to 0 to 2 pi, and outside the interval it's defined based on the 2 pi periodicity. Okay, so now for the a naught, this is just 1 over 2 pi integral from 0 to 2 pi of x dx, and we know that integral of x is just x square over 2 from 0 to 2 pi. So this is just 1 over 2 pi, and then this is 4 pi square over 2 minus 0. So that means 2 pi over 2, which is just pi. Okay, a naught is pi. Now for a1 will be, sorry, for an will be 1 over pi integral from 0 to 2 pi of f of x, and then f(x) is x in this case, So cosine of nx dx, right? So let's integrate this using integration by parts. So 1 over pi, we have x times sine nx by n minus derivative of x is 1, integral of cos is minus sine, so minus minus plus. Again, I have to take integral of sine, so that becomes minus cosine, right? Let me do it step by step. Let me jump it. Okay, so minus integral of this is derivative of x is 1, so integral of cos is, oh, just sine, it's not minus n, I'm sorry. Sine nx over n dx, right? And then 1 over pi, so this is x sine nx over n, and then now integral of sine is minus cos and minus minus plus. Okay, so good. Cos nx over n square. Okay, that's correct, I think. Okay, now from 0 to 2 pi, right? So 1 over pi. So this is just 0 because sine 2 pi n is 0. And cos 2 pi n is, what is cos 2 pi n? That's 1 over n square. And then again, minus, that should be 0. And this should be 1 over n square. So 1 n square, 1 over n square, 1 over n square cancel out. So this becomes 0, right? So a sub n is 0 for all n. Now for b sub n, it should be 1 over pi integral from 0 to 2 pi of x sine of nx dx. Okay, now let's see how we can do that. The same thing, 1 over pi and integration by parts, x. So this is minus cos nx over n minus derivative of x is 1 and then minus cos nx over n dx, right? And then this minus minus, this becomes plus because of that. So 1 over pi x minus cos nx over n. And then after that it becomes sine nx over n square from 0 to 2 pi. Okay? So this is 1 over pi. This becomes minus 2 pi over n, right? Plus 0. And then 0 plus 0. Okay? Right? So this is essentially minus 2 over n. So we get this, right? So b of n is minus 2 over n. So that means this f of x equals to x for x belongs to 0 to 2 pi and 2 pi periodic function. This can be written as f of x equals to a sub 0 is just pi, which is pi, and then after that sum from n equals to 1 to infinity of with 0 cos nx plus sum from n equals to 1 to infinity with minus 2 over n sine of nx, right? And this is just x, and this is valid on 0 to 2 pi. Okay, so x can be written as pi plus sum from n equals to 1 to infinity minus 2 over n sine nx for x belonging to 0 to 2 pi. It's always important to know this domain in which x lies, right? Because the series can be different if the domain was like minus pi to pi. That's why I'm always trying to write it. Okay, so yeah, we got the series for x, right? Now similarly, we can also, in the similar manner, we can find series for x square as well. So the series for x square for x belonging to 0 to 2 pi and 2 pi periodic, it's also essential to know the period, because like let's say if I wanted a like pi periodic function on rather than 0 to pi, that will also be different. So it's important to know that. And yeah, so you can do it the same way and find the following thing. So 2 pi square divided by 3 plus, this is our a naught, and then a n will be 4 over n square cosine of nx, and then b sub n will be sum from n equals to 1 to infinity minus 4 pi over n with sine nx. Okay, this will be our b sub m. Yeah. So this, yeah, you can also get this using the same idea. It just takes some time. So that's why I did it beforehand, and then I'm presenting it to you now. But now, like, you might want to like do all those integrals again and again, right? So isn't there like a different way? Yes, there is. Like while like just like in how in sum we used to find like another sum from the previous sum using like integration by integrating both sides. We can do the same thing over here as well. You know, like you can integrate to get the new series, you can differentiate to get the new series. We can do that. And while integrating or differentiating, the interval in which the series is valid will remain same. Okay. So if I integrate and get a new series, that will be valid in the same interval as the original series was. So let's take this series. T is equals to pi plus sum from n equals to 1 to infinity minus 2 over n sine of nt. And we know that this is valid on 0 to 2 pi. Now let me integrate both sides. Integrate both sides from 0 to x. So I get a new series now if I do that. 0 to x t dt is equals to 0 to x pi dt plus, I can take the integration inside the sum, and minus 2 over n is just a constant. So integration from 0 to x sine of n t dt. Okay, I can do this, and this new series will again be valid on 0 to 2 pi. Okay, yeah. So now this will be t square over 2, so that will be x square over 2 minus 0, which is just 0, and then this will be pi x plus, now over here, sum from n equals to 1 to infinity minus 2 over n. This will be minus cos n t over n, right? And from 0 to x. Okay. Let me write it as x square is equals to 2 pi x plus sum from n equals to 1 to infinity minus 1 over n. I multiplied both sides by 2. And then now this will be minus cos nx over n plus 1 over n, right? Now we have x square is equals to 2 pi x plus sum from n equals to 1 to infinity of minus 1 over n square, right? And then plus we have sum from n equals to 1 to infinity of cosine nx over n square, if I'm not wrong. Yeah? Yeah. Wait, one thing. When I multiplied by 2 on both sides, this should have been 4, no? How did I make it 1? I actually divided by 2. Okay, that was a mistake on my part. That should have been 4, right? Because when I multiply by 2, of course, 2 times 2 is 4. And then now this should be minus 4 n square. Over here also it should be 4 over n square. Okay? I'm just trying to match the other series where there's 4 over n square. So I was surprised. Okay. And then now we know that this is just zeta of 2 times minus 4. So that will be minus 4 times pi square over 6, right? Because we know that zeta of 2 is pi square over 6. Okay. Plus sum from n equals to 1 to infinity 4 over n square and then cosine of nx. Okay. Now over here we actually wanted a Fourier series of x square, right? And then for the Fourier series we have a constant term, we have infinite sum of sine, infinite sum of cosine, right? And this doesn't seem to be something we want, right? Because we only want either constant or sines or cosines. So this is actually a problem over here, and we can easily get rid of that problem because we know what x should be, right? We know we can substitute x as this thing, and then we can write it in terms of like a constant and the series of sine, right? So let's do that. Let's write x as this thing. Copy. So it will be x square is equals to 2 pi and then paste. Yeah. Yeah. And then after that, this is minus 2 pi square over 3 plus sum from n equals to 1 to infinity 4 over n square cosine of nx, right? So we have x square is equals to, now this is 2 pi square minus 2 pi square over 3. I'm grouping the like terms. And now this should be sum from n equals to 1 to infinity. Now 2 pi times minus 2 is minus 4 pi over n. And then sine nx plus sum from n equals to 1 to infinity 4 over n square cos of nx. Okay. And now we know that 3 times 2 is 6 minus 2 is 4. So this is 4 pi square over 3. Let me write the cosine terms first. Sum from n equals to 1 to infinity 4 over n square cosine of nx plus sum from n equals to 1 to infinity minus 4 pi over n sine of nx. Okay. And yeah, and this should be valid on x being on 0 to 2 pi, because I said that the domain will be the same thing as the initial series, and this will also be 2 pi periodic. Okay. Yeah. Okay, so we have got a Fourier series for x square as well, valid on 0 to 2 pi and 2 pi periodic, right? Yeah, and it exactly matches 4 pi square over 3, 4 over n square minus 4 pi over n. So we saw that there's actually a different way, like we can actually get the series for x square without actually doing those three integrals, right? We just had to integrate the series we already had, and this integration was way easier because the other one would have so much of integration by parts, whereas this one was actually easier. So if we can get from here to here using integration, right, then that definitely means we should be able to go the other way using differentiation, no? So let's try that if we can get the series of x from the series of x squared in differentiation. And that's what I mean by messing around, like just trying different things, like doing things that make sense and that should be true, and actually seeing if it's true or not, and then to see like what we actually, if there are some new things that should be true to make it true, something like that, that's what is messing around is for me. So now let's differentiate this and see if we can get the series of x squared. Okay. So now differentiate. Okay, yeah. So we are gonna first of all differentiate this, right? And if we differentiate left hand side, we are gonna get 2x, and the constant is gonna go to 0. And over there, this cosine term is gonna be the negative sine nx with n, and sine nx term which is gonna be like cosine of nx with n, right? Notice that in the last term the n cancel out, and we will just have a sum of the cosine only, and that's why, because the cosine is not there in the original series, that's how we discover something new, and I will show you. Okay, so if I, let's say, differentiate with respect to x, we get 2x is equals to 0 plus sum from n equals to 1 to infinity 4 over n square, and then minus sine nx times n plus n equals to 1 to infinity 4 pi over n cosine of nx with n cancels out, and with the n square, one of the n cancels out. So we have 2x is equals to 4 times sum from n equals to 1 to n square, a minus 1 over n sine of nx plus, and then this is minus 4 pi sum from n equals to 1 to infinity cosine of nx. Okay. And now this means, so x is sum from n equals to 1 to infinity minus 2 over n sine of nx plus minus 2 pi sum from n equals to 1 to infinity cosine of nx. Okay, and this is for x being on 0 to 2 pi, right? Note that actually not x cannot be like just 0 or just 2 pi. I mean, at those point, like the conversion, the point of convergence is different, can be different. And so yeah, so that's why I'm not giving I'm giving, that's why I'm giving round bracket. Okay, so yeah, so we found the series, right? The series for the x over here. And notice that this time it's different. Like this time, okay, we do have the same thing for the coefficient of sine, but earlier we didn't have cosine term, and we had a constant pi, right? And this time that's not the case. We don't have a constant pi. So I mean, okay, so from here we can infer that this term should actually be pi, right? Because only then, if that's pi, then only then it's gonna match the original series, right? And it should match the series. Like every function has a unique Fourier series. That's why it should match. So that means over here, this minus 2 pi, sum from n equals to 1 to infinity, cosine of nx is equals to pi, right? And then sum from n equals to 1 to infinity, cosine of nx is equals to minus half. And we have the series. You can also prove this series using, like, by writing cosine as the real part of e to the power inx, and then summing it up using geometric series and things like that. But over here, this series is interesting, and like we know that this should be true, because if it isn't, then like, I mean, it just should be right, because we got a series for x by differentiating, and then because the series is unique, they should be same. Yeah, I mean, otherwise, this everything is just like there's some problem with it, right? So there isn't a problem, and this should be true. And if this should be true, notice that over here x should be between 0 to 2 pi, right? So that means I can take x as pi, right? Because pi is between 0 to 2 pi, because pi belongs in 0 to 2 pi, right? And then what we get is sum from n equals to infinity, cosine of n pi is minus half. Okay, so cosine of 1 pi is minus 1. Cosine of 2 pi is 1. Cosine of 3 pi is minus 1. Cosine of 4 pi is 1. Cosine of 5 pi is minus 1. Cosine of 6 pi is 1. So this series over here is actually minus half. And this should be true for the Fourier series to be unique. Fourier series for x to be unique. Right? And then like, yeah, like this is the metric series with like r minus 1, and because this r is 1, we don't really know about the convergence, because for the convergence this should be less than 1, and if it's more than 1, that's divergence. So for 1 we didn't know what to do, but it turns out in this case it should be a convergent series, but it's not really clear how in the normal sense of convergence, like it should approach the limit, like the limit minus the last term should, like last term of the series, like the partial sum should go down and down and down. But over here that's not happening. Like the normal convergence isn't really making sense over here. But again, in some sense it should converge, and it should be minus half, because otherwise this whole thing just fails. Like otherwise this whole idea of integrating and differentiating a series to get new series will just fail. So this should be true. And yeah, I think with this, I think I have given you a new perspective on why this thing should be true, even though before this I never really believed it should be true. But now I think I'm kind of convinced that this should be true for many good things to be true. I don't know if you know what I mean. Okay, yeah. So that's it for today, and let me just summarize. So first of all, we tried to find the Fourier series of x using 3 different integrals, and then we found the Fourier series of x, right? It was pi plus sum of minus 2 over n sine nx. And we also found the Fourier series for x squared, though I didn't show you explicitly. And then we wanted to find the second series from the first one using integration, which we did, right? The tiny thing that we needed to know was that we could substitute a series for x over here, which we did. And then we got the new series, but then we wanted to go back as well, which is actually our messing around thing. And when we were trying to go back, we actually found that this thing should be pi, and that makes this sum minus half. And then because of that, we got that thing, we got the series. Actually, let me give you one more thing. The sum from n equals to 1 to infinity of sine nx is actually half of cot x over 2. From here also we can get the same thing, I guess. Because over here, let's say if you plug in, and you can get this from by writing sine as imaginary part of e to the pi n x. Okay, you can get it that way. And over here, let's say if x is pi over 2, sine of n pi over 2 is 1 for n equals to 1, and then 0, and minus 1, and then 0, plus 1, 0, minus 1, 0, so on. And right hand side is half of cotangent of pi over 4. So over here, we can see that 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1. This thing is just half times 1, which is half, which is exactly the same idea. Like this thing over here, we got minus half, where it begins with minus 1, and if it begins with 1, and then it's half. So yeah, pretty crazy and interesting stuff. And guys, definitely you need to believe from now that this is true. I don't know how, why, but yeah, you need to believe that this is true. I mean, I gave you why, because this is needed for some results to be consistent, right? So that's it for today, guys, and I definitely hope you enjoyed this video, and definitely watch other 4 videos on the art of messing around. This is my favorite playlist, and I definitely believe all of you will enjoy this. Thanks for watching, and I look forward to seeing you in the upcoming videos too.